The first light of the universe never went out. It did not fall into darkness, and it did not vanish into some faraway place. It is still here, travelling through the space around us, silent, cold, and older than every star that has ever been born. Welcome to Drift into Quiet Knowing. Tonight we will follow a question that seems very simple, yet opens up almost the entire history of the universe. Where did the first light of the universe go after 13.8 billion years? If that light once filled everything, why is the night sky dark? If it still exists, why can our eyes no longer see it? The answer is not that the light has died. In physics, light does not age the way humans do, but as space expands, the wavelength of light is stretched. What was once the blazing light of a young universe slowly cooled, shifted out of the range that human eyes can see, and became the cosmic microwave background, a fossil layer of light that covers the entire sky. What is especially remarkable is that the oldest light we can observe did not come from the first stars. It is far older than the stars. It was released when the universe was about 380,000 years old, when the original plasma fog began to clear. Electrons and protons combined into neutral atoms, and photons were finally able to travel long distances without constantly colliding with charged particles. On this journey, you will understand why the early universe was once like a glowing but hazy ocean, why the first light is no longer visible like today, why it comes from every direction instead of sitting at some distant edge of space, and why the tiny ripples in that light became the clues that eventually led to galaxies, stars, planets, and, in the end, to us. So stay with this slowly. Let your eyes rest. Let your mind open in silence, and together, let us follow the cold whisper of the oldest ancient light still left over from the dawn of the universe. If we want to trace the first light of the universe, the most important thing is to let go of an image that can easily mislead us. That light was not like a lamp beam switched on at some point, then flying straight through darkness for 13.8 billion years until it reached us. The early universe was not a black stage where one lamp had just flashed on. It was the flame itself. Space, matter, and radiation were blended together in a hot, dense, chaotic state, so extreme that there was no clear path for light to travel through. Imagine the entire young universe as a room with no walls, no ceiling, and no outside. But inside that room was a glowing fog. Not a cold fog like a morning mist on Earth, but a fog so hot that atoms could not yet exist in a stable way. Light was everywhere. Energy was everywhere. But light could not create a clear image because it was constantly being blocked, scattered, and redirected by free electrons drifting through the original plasma sea. This is the first point we need to hold firmly. The early universe was not lacking light. It was lacking transparency. When we look through clear air, light from a distant mountain, a star, or a planet can pass through space and reach our eyes. But when you stand inside a thick fog, the light is still there, and it may even be very strong, yet everything becomes opaque. You cannot see the horizon. You do not know where the true source of the light is. Each tiny water droplet in the fog redirects the light again and again, causing the image to lose its structure. The young universe was similar, except its fog droplets were not drops of water. They were charged particles, especially free electrons. In a plasma state, electrons were not yet locked inside atoms. They moved freely through expanding space. Photons, the tiny packets of light, could travel only a very short distance before colliding with electrons again. After each collision, the photon changed direction. It could not keep flying straight across the universe like a messenger carrying information from one place to another. It was like someone trying to walk through an extremely crowded square, getting pushed in a new direction with every step. There was motion, there was energy, there was light, but there was not yet a free journey. So when we talk about the first light of the universe, we have to be very precise. It was not the first light in the sense of the very first photons appearing right after the Big Bang. Those extremely early photons existed in an environment that was too hot and too dense, where they kept interacting with matter. The first light that humans can observe today is the light that was released when the universe became transparent. It is the oldest light that can still carry direct information to us through electromagnetic radiation. For a more familiar image, imagine standing inside a giant pool of milky water. There may be a light source on the other side of the pool, but the cloudy water scatters the light everywhere. You cannot see the shape of the source, you cannot see distance, and you cannot reconstruct a clear picture. Only when the particles that make the water cloudy settle down can light travel far enough to form an image. In the universe, that settling down did not happen because dust sank to the bottom. It happened because the temperature gradually dropped as space expanded. The more the universe expanded, the more the average energy in each region of space decreased. The temperature fell. When it was still too hot, every time an electron tried to join with a proton to form a hydrogen atom, the high-energy radiation around it could easily break that bond apart. Atoms could not survive for long. Everything returned to plasma. But as time passed, space grew larger, the universe became cooler, and at a very important stage, electrons began to stay around nuclei. From that point on, the first neutral atoms formed on a large scale. This event is often called the era of recombination, but that name can be a little misleading, as if electrons and protons had joined before and were now simply meeting again. In reality, this was the stage when the universe became cool enough for electrons and protons to bind together in a stable way and form neutral atoms. And when most electrons were no longer wandering freely through the plasma, photons were no longer scattered constantly as before. Suddenly the universe opened up, not like a door opening somewhere in space, but optically. It became transparent to light. That moment did not happen in a single short second like flipping a switch. It was a transitional period in the history of the universe. But from our enormous distance in time today, it looks like the first dawn that physics allows us to observe. Before that, light was trapped in the hot fog. After that, photons could leave the last region of matter that had scattered them and begin a long journey, almost unobstructed through expanding space. That is why astronomers say we cannot directly see the moment of the Big Bang with ordinary light. It is not simply because our telescopes are not large enough. It is because before the universe became transparent, light could not carry images across long distances. There was a real physical curtain, a natural limit in the history of observation through light. That curtain was not a solid wall of matter. It was an era when photons were scattered too often to preserve clear information. This makes the question, where did the first light go, much deeper? The light we are searching for is not an object that left one place and vanished into another. It is the remnant of a universe-wide state. When the universe changed from opaque to transparent, light was released everywhere. There was no single center shooting light outward. There was no explosion point sitting in the middle of empty space. All of space itself was hot, dense, and full of radiation. When the plasma fog cleared, light began traveling freely from every region of the young universe. If you have ever seen sunlight breaking through clouds after rain, you can feel a small part of this idea. The sun was shining all along, but the clouds scattered the light. When the clouds thinned, the landscape appeared. In the early universe, there was no sun behind the clouds. The universe itself was the light source, and when the cloud of free electrons disappeared, light was not released from only one direction. It was released from every direction, from every region, as if all of space had become see-through at once. But there is something very important to notice, that light, when it was first released, was not like what we detect today. When the universe was a few 100,000 years old, its temperature was still several thousand degrees Fahrenheit, or a few thousand Kelvin, much hotter than the surface of any cold object in everyday life. The radiation belonged to a universe that was still young and warm. If some impossible creature could have existed there and observed with eyes in this imagined way, it would have seen a brilliant, almost uniform environment, with no stars, no galaxies, and no separate points of light like the night sky today. No stars were shining at that moment. The first stars appeared much later, after matter began clumping together under the pull of gravity. So the oldest light is not starlight. It is older than stars. It comes from a time before the universe had familiar structures such as galaxies, galaxy clusters, planets, or interstellar dust. It is the light of the universe itself, from the moment the universe had cooled enough to become transparent. We can call it a baby picture of the universe, but even that phrase has to be understood carefully. It is not a picture taken from the outside, because there is no simple outside where a camera could be placed. It is the layer of light reaching us from the farthest time at which light could travel freely. When we look very far in any direction, microwave telescopes do not see a physical wall. They reach the light emitted when the universe first became transparent. That layer of light is called the cosmic microwave background. The name may sound dry, but its meaning is beautiful. Background means it does not come from one separate object, such as a star or a galaxy. It is the shared light background of the entire observable universe. Microwave means that today its wavelength has been stretched into a range that human eyes cannot see, but scientific instruments can measure. Cosmic means it is not a local phenomenon near Earth, not light from the atmosphere, not noise from a device, but a trace of the entire history of expanding space. So why did that once hot light become cold microwaves? The answer lies in the expansion of space itself. This is one of the most beautiful and hardest ideas to grasp in cosmology. Light does not need to get tired after travelling for too long. Photons do not slow down in a vacuum, because light in a vacuum always travels at the speed of light. But the wavelength of light can be stretched when the space it travels through also expands. When the wavelength becomes longer, the photon's energy becomes lower. When the energy becomes lower, the radiation corresponds to a colder temperature. Imagine a wave line drawn on a strip of elastic fabric. If you stretch the fabric, the distance between the wave crests increases. The wave does not need to decide to stretch itself. The background it rests on has changed. In the universe, space is not actual fabric, but this image helps us feel what is happening. As the universe expanded over billions of years, ancient light was stretched along with that expansion. What was once radiation from a hot universe became extremely cold radiation, only about minus 455 degrees Fahrenheit, or 2.7 Kelvin, just a little above absolute zero. This is exactly why the night sky appears dark to our eyes. The first light still exists, but human eyes cannot see microwaves. We can see only a very narrow band of the electromagnetic spectrum, called visible light. The universe is not completely silent in radiation. It is giving off a very weak, very even microwave background from every direction. If our eyes could see microwaves with the right sensitivity, the darkness of the sky would no longer look like empty blackness. It would have a cold, smooth, ancient glow, like a mist of light that has cooled after almost the entire lifetime of the universe. But one more thing needs to be said to avoid another misunderstanding. The cosmic microwave background is not flying around us like bits of light debris separated from the universe. It fills space, and its photons pass through us constantly. They are too weak for our eyes to sense, but with the right receivers, humans can measure them. In every tiny volume of about 0.061 cubic inch, or 1 cubic centimetre, of space, there are many photons from this background radiation. They are the most widespread legacy of the young universe, quieter than any flame, but larger than any galaxy. When we think about that, the darkness of the night sky becomes something very different. It is no longer absolute absence. It is a veil that human eyes cannot read. Behind that blackness lies an extremely ancient thermal record. Each microwave photon carries within it the story of its last scattering, when it left the original plasma and began travelling through space. It does not remember the way humans remember, but its physical state preserves information: temperature, direction, wavelength, and the tiny differences between one region and another. Those tiny differences are an important part of the story. If the cosmic microwave background were absolutely identical in every direction, the later universe would have had a very hard time forming the structures we see. But it is not perfectly uniform. It is almost uniform, with only extremely small temperature fluctuations at the level of parts per million. Those gentle ripples in the young universe are traces of the earliest density differences. Places that were slightly denser could pull in more matter through gravity. Over hundreds of millions and then billions of years, those almost invisible differences were amplified into enormous cosmic webs of galaxies. Here, the first light does not only answer the question of where it went, it also answers a deeper question. Why did the universe not remain a smooth fog forever? Why do we now have spiral galaxies, galaxy clusters, gas clouds, massive stars, rocky planets, and eventually living beings who can ask questions about the first light? In the tiny ripples of the cosmic microwave background, we see the original seeds of structure. They were almost unimaginably small. but they were enough for gravity to work over a very long time. That is a gentle but powerful lesson from cosmology. Small differences, when supported by time and the laws of nature, can become the entire architecture of the universe. A tiny temperature difference in ancient light can correspond to a place where matter was slightly thicker or slightly thinner. From there, gravity began to pull, gather, slow, drop, and condense. Not in one dramatic instant, but with patience stretching across billions of years. The universe did not build galaxies through one loud explosion, but through small differences amplified by time. If we place ourselves in the position of an astronomer reading a map of the cosmic microwave background, we are not just looking at a beautiful image. We are looking at extremely precise numbers. Each point on the map represents a slightly different temperature. The colours in popular images are not the true colours that human eyes would see. They are a way for scientists to magnify the differences so we can recognise them more easily. The warmer and colder regions differ only by an incredibly tiny amount compared with the overall background. But in science, sometimes the most subtle thing reveals the most. A map like that allows us to test major ideas about the universe. It helps determine the age of the universe, the proportions of ordinary matter, and dark energy, the geometry of space on large scales, and how structure formed. All of this does not come from vague guessing, but from measurements of the radiation left over from the era when the universe became transparent. When a theory of the universe is correct, it has to explain why that background light has its temperature, why it is almost uniform, and why it contains tiny ripples in the measured pattern. This is why the cosmic microwave background is often considered one of the strongest pieces of evidence for the hot Big Bang model. If the universe was once much hotter and denser in the past, we would expect leftover radiation to remain after it cooled and expanded. That radiation should appear from every direction, have a spectrum very close to an ideal blackbody, and have a very low temperature today because of cosmic redshift. Those expectations match observations in a profound way. In other words, the microwave sky is not just a strange phenomenon, it is the thermal fingerprint of cosmic history. However, scientific accuracy also requires that we do not overstate what we know. The cosmic microwave background does not let us see through everything, all the way to the absolute beginning. It is the observational limit for light, not the absolute first page of reality. Before the time when the universe became transparent, we can still study things indirectly through mathematics, through traces in large-scale structure, through particle physics, through the hypothesis of cosmic inflation, and perhaps in the future through primordial gravitational waves if they are reliably detected. But with electromagnetic light, this is the farthest curtain we can touch. That makes the first light both near and far. Near, because microwave photons are passing through the space around us right now. Far, because they come from a time when the universe was so young that no star had yet ignited. Near, because we can measure it with instruments on Earth and satellites in space. Far, because it carries the mind almost to the observable edge of time. It is like a letter written without words, sent not by a person, but by the entire early universe. Let us pause for a moment with that image. Whenever we say light has travelled for 13.8 billion years, it is easy to imagine it crossing an empty space that had already existed from the beginning. But in modern cosmology, space itself is also changing. The distance between very far away regions increases over time. So the journey of ancient light is not just a journey through space, it is a journey through a space that is growing. The light is stretched not because it is weak, but because the universe it lives in has changed size on a vast scale. That is the central answer to the whole story. The first light did not disappear. It was transformed by the expansion of space. It was once the light of a hot universe, and then it became a cold microwave background. It was once trapped in a plasma fog, and then it was released when neutral atoms formed. It once could not carry images far, and then it became the oldest map of the sky. And today, after nearly the entire history of the universe, it still surrounds us like a very low, very cold, very even whisper, holding the memory of the physical dawn of everything. So if tonight you look up at the sky and see darkness, remember that the darkness is not simply emptiness. Your eyes are resting before one very small part of the light spectrum. Beyond the range human eyes can see, the universe still preserves an ancient layer of light. It is not brilliant like stars. It is not warm like the sun. It does not stand out like a galaxy. but it is the light that existed before all of those things. It is the deepest background behind every astronomical image we love. And when we understand this, the original question changes. We no longer ask where the first light went as if it were a lost object. We begin to realize that it went in every direction, through every age, along with the expansion of space, through the time with no stars, then the time when the first galaxies formed, then the time when heavy elements were created inside stars, then the time when rocky planets cooled, until there were eyes and instruments delicate enough to recognize it. It did not leave the universe, it became part of the universe's background. From here, our journey can go even deeper. If the first light we can observe began traveling freely when the universe became transparent, then the next question is, how did that moment of transparency actually happen? Why did electrons joining with protons change the entire visibility of the universe? And how could a hazy sea of plasma become a space where light began to carry information across great distances? To understand that, we have to step into the moment when the universe truly opened its eyes for the first time. From that moment, we can imagine the universe passing through a very quiet but enormously meaningful change, from an opaque sea of light into a space that could carry light across great distances. There was no new explosion. There was no single streak of light tearing through the darkness. There was no razor-sharp boundary cutting before and after in two. There was only the patient cooling of the entire universe as space continued to expand, the density of matter decreased, and particles that had once drifted freely began to find a more stable state. What is astonishing is that this event happened not because light suddenly became stronger, but because the universe became less able to block it. Before that, photons, the particles of light, were constantly scattered by free electrons. It was like a person trying to move through an extremely dense crowd, only taking a few steps before being bumped and pushed in a new direction. But when electrons joined with protons to form neutral hydrogen atoms, the crowd of free charged particles thinned dramatically. Light suddenly had room to keep going, and from that moment on, those ancient photons began a journey so long that almost the entire history of the universe now lies behind them. To understand this more clearly, imagine a gigantic glass room filled with hot steam. When the steam is still thick, everything inside the room is only a hazy brightness, with no clear outlines. You know there is light, but you cannot see through it. Then the room slowly cools, the steam condenses and the air becomes clearer. Layer after layer of haze quietly disappears, and at some point, not because new light has been added, but because the obstacle is withdrawn, you begin to see the other side. In the young universe, that other side is the oldest sky that science can observe through light. There is a very important detail here that needs to be said slowly and precisely. When the universe was about 380,000 years old, its temperature had dropped to about several thousand Kelvin, which is several thousand degrees Fahrenheit. That temperature was still extremely hot compared with everyday life, but it was low enough that electrons were no longer easily stripped away from atomic nuclei right away. Protons could hold electrons and form neutral hydrogen atoms. When matter shifted from a plasma state full of free charged particles into a state with many more neutral atoms, its ability to scatter light dropped sharply. The universe did not become transparent because light changed its nature, but because the environment around the light changed its nature. We can compare this to the difference between walking through a dense forest and walking across an open field. In the forest, you cannot see far not because your eyes lack the ability to see, but because trunks, leaves and branches keep blocking your view. In an open field with the same eyes and the same light, you can see much farther. In the early universe, free electrons were like countless invisible tree trunks to photons. When they became locked inside atoms, the scattering forest thinned out, and light could travel across an immense distance. But we should not imagine this as a perfectly thin boundary, where 1 second earlier the universe was completely opaque, and 1 second later it was completely transparent. In cosmic physics, many processes happen according to probability and unfold over a period of time. The last scattering of photons did not happen all at once like a bell ringing at a single point. Some photons were released a little earlier, others a little later. But on the scale of cosmic time, that era forms an extremely ancient layer, an observable surface often called the surface of last scattering. It is the farthest layer of light in the past that we can see directly through electromagnetic radiation. The phrase surface can also be misleading if we understand it too simply. It is not a wall of matter standing somewhere out there. It is the past limit of our vision through light. When we look very far in any direction, we are looking back in time. Light from the moon takes more than 1 second to reach our eyes. Light from the sun takes about 8 minutes. Light from distant galaxies may take millions or billions of years. And when we look so far that the light comes from the time when the universe was only about 380,000 years old, we encounter the cosmic microwave background, the trace of the moment when the universe had just become transparent. This means that ancient light does not come from a lamp at the edge of the universe. It comes from the state of the universe itself, when all observable space was once far hotter and denser. Every direction in the sky leads us back to a different region of the young universe, where a photon left its final scattering event. So with the right measuring equipment, we do not see a separate point of light. We see a microwave background layer covering the entire sky. It comes from every direction, almost evenly, like a thermal fingerprint spread across space. Right here, the question, where did the first light go, begins to have a clearer answer. It did not go to one separate place. It did not gather into a treasure chest of light in some distant corner of the universe. It also did not vanish like a candle being blown out. When the universe became transparent, light became free everywhere, and over the next 13.8 billion years, the expansion of space stretched that light, cooled it, and transformed it from the hot radiation of the young universe into the cold microwaves we measure today. Let us pause at the word stretched. It is a gentle word, but it contains one of the deepest truths in cosmology. Light is an electromagnetic wave. Each photon is associated with a certain wavelength. The shorter the wavelength, the higher the energy. The longer the wavelength, the lower the energy. When space expands, the distance between the wave crests of light travelling through that space is stretched as well. The photon does not slow down. Light in a vacuum still travels at the speed of light, but its wavelength becomes longer and its observed energy becomes lower. That is cosmic redshift. A simple image can help us feel this. Imagine drawing many evenly spaced wave marks on a soft rubber strip. At first, the marks sit close together, then you slowly stretch the rubber strip. The marks do not move by themselves in a separate way. The rubber background between them is lengthening, increasing the distance between the marks. Ancient light is similar. No hand grabbed it and pulled it longer. The space it travelled through expanded, and that expansion stretched its wavelength over billions of years. When it was first released, that radiation corresponded to a universe that was still hot, about 4,940 degrees Fahrenheit, or about 3,000 Kelvin. Today, because of cosmic expansion, the effective temperature of the cosmic microwave background is only about minus 455 degrees Fahrenheit, or about 2.7 Kelvin, just a little above absolute zero. This is why it no longer lies within the range of light human eyes can see. Our eyes evolved to see a very narrow band of the electromagnetic spectrum, mostly suited to sunlight reflected from the world around us. But the cosmic microwave background has been stretched into the microwave range, where human eyes are completely silent. So when we look up at the night sky and see darkness, we are not seeing the full truth of light. We are only looking through a limited biological organ. The sky appears black because most of the ancient background light is not in the visible range. If we had a natural sense sensitive to microwaves, and if that sense were delicate enough to distinguish extremely cold radiation, the sky would not be completely dark. It would appear as a faint, almost even glow, very cold, very ancient, not light from a star, but the thermal echo of the early universe. This also explains why the first light is present in every direction, but does not make the night shine brightly. The energy of those photons has decreased greatly because their wavelengths have been stretched. They do not have enough energy to stimulate our retinas the way visible light can. They do not form familiar images such as stars, clouds, mountains, or oceans, but to microwave receivers and specialized telescopes, they are a real signal, measurable, structured, with temperature, with a spectrum, and with enormously deep cosmological meaning. If that light had simply weakened with distance, the story would be different. but the unique point is that it was transformed by the expansion history of the universe itself. Each photon of the cosmic microwave background is like a tiny letter, carrying the seal of the past. Along the way, the letter was not erased, but its paper was stretched along with space. By the time it reaches us, the message is still there, only written in a different wavelength. Instead of the hot light of a young universe, we read it as the cold microwave background of a much older universe. From a scientific point of view, this is a rare gift. The cosmic microwave background does not only tell us that the universe was once hot, it also allows us to measure how uniform the early universe was. When satellites and telescopes measure the entire microwave sky, they find that the background temperature is almost the same in every direction. That sameness shows that the young universe was very uniform on large scales, but the phrase "almost the same" is extremely important. It was not perfectly uniform. It had very small temperature fluctuations, and those fluctuations became the seeds of every later structure. Picture a very flat sheet of fabric under soft light. From far away, it looks almost completely smooth, but with a sensitive enough instrument, you can see tiny ripples on the surface, places rising or dipping so slightly that the naked eye would almost never notice them. In the cosmic microwave background, small temperature ripples play a similar role. They reflect regions with slightly different matter densities in the early universe. Places that were a little denser had a little stronger gravity, pulling more matter toward themselves. Across immense time, those small differences grew into galaxies, galaxy clusters, and the cosmic web. This is one of the things that makes the first light so moving. It is not only ancient light, it is the first draft of a structured world. Within it are the faint signs of where matter would gather, where the first stars would ignite, where heavy elements would be created inside stars and in stellar explosions, where clouds of dust would become planets, and, much later, where a small planet could have oceans, rocks, an atmosphere, and life capable of looking back toward its own origin. But we have to keep the humility of science. Not every tiny hot or cold spot on the microwave map can be pointed to directly and declared, this is exactly where one particular galaxy will form. The universe develops in a more complex way than that. The initial fluctuations are background conditions, the statistics of structure, the seeds of density distribution. Gravity, dark matter, baryonic gas, radiation, the expansion of space, and many other physical processes all take part in the later evolution. But even with that complexity, the basic connection remains clear. From extremely tiny unevenness in the young universe, the large-scale structure of the cosmos gradually formed. If we return to the original question, we can see that it has expanded. The first light is not only where in the sense of location, it is where in our history. It lies behind every galaxy that telescopes can observe. It lies behind the age when the first stars lit the darkness. It lies behind the creation of carbon, oxygen, iron, and the elements that make up rock, water, blood, and breath. It is not only the background of the sky, it is the background of the material story that led to everything familiar. There is a beautiful paradox here. The first light is very cold today, but it was born from a very hot universe. It is very weak, but it is one of the strongest signals of evidence for cosmic history. It is almost uniform, but its tiny differences help explain why the universe is not monotonous. It is invisible to the eye, but thanks to it, human intelligence can see farther than any natural eyes. It does not speak in language, but scientists can read in it the age of the universe, the contents of the universe, and traces of the initial conditions. When we hear the age of 13.8 billion years, it is easy to treat it as a distant, unfamiliar number. But in the story of ancient light, that number has a very specific meaning. It is the time the universe has spent expanding from its early hot, dense state to its present state. The light released when the universe was only 380,000 years old has travelled through a history so long that every civilization, every living species, and every mountain on Earth is only a very late passage in that journey. Before there was the sound of ocean waves, before forests existed, before golden dust lay inside veins of rock, that radiation had already begun to travel. But we also should not say that a photon travelled through 13.8 billion years too simply, as if it were only flying through a static space. Space expanded while the light was moving. Regions that were once much closer together in the young universe can now be far more distant from us because of the expansion of space. So when we say ancient light comes from very far away, we are talking about a cosmological distance where look-back time, the expansion of space, and redshift are closely connected. This is not the path of a bullet through a still room. This is the journey of light through a universe that is growing. That very growth is what made the background radiation become microwaves. If the universe did not expand, ancient light would not have been stretched in the way we see today. But because space expands, wavelength increases enormously. Light that once corresponded to a temperature of about 4,940 degrees Fahrenheit, or about 3,000 Kelvin, is now only about minus 455 degrees Fahrenheit, or about 2.7 Kelvin. This cooling is not a poetic metaphor. It is a measurable consequence of the expanding universe model. When we measure the spectrum of the cosmic microwave background, we find that it is very close to a perfect blackbody spectrum at that temperature. This is one of the most beautiful observational results in modern physics. The term blackbody may sound strange, but its scientific meaning is very important. An ideal blackbody absorbs and emits radiation in a spectral shape that depends on temperature. The cosmic microwave background has a spectrum that is almost like an ideal blackbody, which fits the fact that it was once in thermal equilibrium in the hot early universe. More simply, that radiation is not like random chaotic light from many modern sources mixed together. It carries the very distinctive thermal shape of a universe that was once hot, dense, and strongly interactive between matter and light. This helps us distinguish the cosmic microwave background from other kinds of noise or light. Earth has an atmosphere. Galaxies have dust, gas, stars, radio sources, and many things that emit radiation. But the background radiation has an all-sky pattern, a special thermal spectrum, and a deep uniformity that cannot be explained as a small local phenomenon. It is a trace of the entire universe. To observe it precisely, scientists have to remove signals from our own galaxy, from dust, from radio sources, and from the motion of the observing system itself. After they do that, the ancient layer of light is still there, persistent and consistent. This truth gives darkness more depth. When human eyes look at the night, space feels empty. But science shows that space is not silent in an absolute sense. Within it are background radiation, microwave photons from the time when the universe became transparent, particles and fields, distant light from galaxies, and remnants of the past. Darkness is not the denial of light. It is a place containing forms of light our eyes were not made to see, and among them, the cosmic microwave background is the oldest form of light we can measure through electromagnetic radiation. We can imagine each photon of the background radiation as a messenger that has crossed a changing universe. When it left its final scattering event, there was no Milky Way as we know it today, no Sun, no Earth. It travelled through the earliest ages when gas began to gather, through the time when the first stars were born in cosmic darkness, through the formation of galaxies, through stellar explosions that enriched space with heavy elements, through the birth of our planetary system. Finally, a very small part of that stream of photons met human measuring instruments, and we understood that we were hearing a whisper from the time when the universe was still very young. What is special is that this light does not carry a story through familiar images. It does not show us a first star with clear outlines. It does not show us a planet. It does not show us a face. It shows us the statistical state of the entire young universe. It speaks through temperature, spectrum, direction, and small fluctuations. And for that reason, it has a special kind of honesty. It is not rewritten by our imagination. It is leftover physical data, measured, tested, compared, and used to challenge scientific models. If there is one thing to remember clearly, it is this. The first light we can observe is not light that was born and then disappeared, but light that was once trapped in an opaque universe, released when the universe became transparent, and then stretched by the expansion of space into a cold microwave background covering every direction. That single sentence connects the primordial plasma, the first hydrogen atoms, the surface of last scattering, cosmic redshift, the cosmic microwave background, and the night sky we see today. From here, whenever we hear the question, where did the first light go? We can answer with the calmness of science. It is everywhere, but no longer in the form our eyes can see. It travelled with space as space expanded. It cooled, its wavelength lengthened, and its energy decreased. It became a cold, almost uniform background glow, quietly passing through us at this very moment. And in that quietness, it still preserves tiny ripples, the first signs of a universe that would give birth to stars, galaxies, planets, and minds able to ask questions. Perhaps this is why the story of the cosmic microwave background always has its own kind of beauty. It does not need violent scenes to be astonishing. It only needs one deep truth. The oldest light does not belong to the past in the sense of being dead. It still touches the present. The universe's past is not locked away in some unreachable distance. Part of it is arriving to us as microwave photons. Every precise measurement of the microwave sky is a way of listening to history, not with ears, not with naked eyes, but with tools sensitive enough to detect the remaining warmth of the cosmic dawn. And when we understand it this way, we step into a new layer of meaning. The first light does not only answer a question about origins, it also reminds us that the universe can preserve traces of itself. A hot, dense, opaque state from more than 13 billion years ago still left behind measurable radiation today. An era before stars existed can still be read through modern science. A small change in temperature in the early universe can still be connected to the largest structures in the cosmos. That makes the night sky not only vast but full of memory. So from the moment the universe became transparent to the time that light was stretched into microwaves, we see a very clear chain of cause and effect. The universe expanded, so it cooled. The temperature dropped, so electrons could join with protons. There were fewer free electrons, so photons were scattered less. Freed photons could travel far, so they formed the oldest light we can observe. Space continued to expand, so the photons' wavelengths became longer. Longer wavelengths made that light become cold microwaves. And today, that microwave background still covers the entire sky, like silent evidence that the first light never truly disappeared. Now let us go deeper into the strangest part of this journey. The first light did not disappear, but it also no longer looks the way it did when it first became free. It was stretched by the universe itself, not stretched by a force like a hand pulling on a rope, not stretched because the light grew weak like a flame about to go out, but because the space that the light travelled through expanded over billions of years. As the background of the universe grew larger, the waves of light within that background were stretched along with it. And when the wavelength becomes longer, the energy of the light decreases. That is why light that once belonged to a hot young universe has now become a cold microwave background only slightly above absolute zero. This is very important, because if we misunderstand it, we might imagine that ancient light became tired after such a long flight. But light does not age the way humans age. A photon does not have its own little clock to feel how long it has been travelling. In a vacuum, light still travels at the speed of light. It does not slow down because the distance is long. It does not wear away like a stone rolling across a desert. What changes is the measure of space itself. As space expands, the distance between the wave crests of the photon also expands. Light does not lose its nature, but it changes colour, changes energy, and moves into a different region of the electromagnetic spectrum. Picture a very soft rubber cloth with a small wave drawn on it in ink. At first, the wave crests are close together. Then we slowly stretch the cloth wider. The ink line is still the same ink line, but the distance between the wave crests has increased. Nobody is holding each crest and pulling it separately. The surface that the wave rests on has expanded. With the ancient light of the universe, something similar happened in a much deeper way. Space is not rubber, but the expansion of space makes the wavelength of light travelling through it grow longer throughout cosmic history. When that light first left the original plasma fog, the universe was still hot, at several thousand degrees Fahrenheit, or several thousand Kelvin. To put it in an image we can feel more easily, it was not a cold darkness with a few bright dots. It was a warm, glowing, almost uniform field of radiation. The light back then had much more energy than today's microwave background. Its spectrum matched a young universe that was more than 1,000 times hotter than it is today. But then space kept expanding. Billions of years passed. The wavelengths kept growing longer, the energy kept dropping. What once belonged to the light of a warm, brilliant universe gradually drifted out of the range human eyes can see, passed through infrared, and became microwaves. Here, we should make a very clear distinction between two kinds of redshift often mentioned in astronomy. When an ambulance moves away from you, the sound of its siren becomes lower because the sound source is moving away. With light, relative motion can also change the wavelength, and we call that the Doppler effect. But the cosmic redshift of the cosmic microwave background is not only the story of an object moving away through space that already exists, it is deeper than that. It is the stretching of light because space itself between distant regions is expanding. Space is not standing still while photons fly through it, as if through a fixed room. The cosmic room is growing while the photons move through it. So when we say the first light was redshifted, we are not only saying it became redder, in the sense of the colour red that human eyes can see. The word red here is a historical term from spectroscopy. A longer wavelength shifts toward the red side of visible light. But ancient light has been stretched far beyond red. It passed beyond infrared and entered the microwave region. That is why our eyes cannot see it, even though it is present in every direction. Human eyes are not instruments for measuring the entire electromagnetic spectrum. They only open a very small window onto nature's vast ocean of light. If human eyes were like a radio that could receive only one narrow channel, then the cosmic microwave background would be broadcasting on another channel, one that's very cold and has very long wavelengths. It does not awaken the retina the way light from a candle, the sun, or a star does. But with microwave antennas, radio receivers, and specialized satellites, that background glow appears clearly. It does not appear as an image with mountains, oceans, or stars. It appears as an extremely delicate thermal map of the sky, almost uniform but with tiny ripples so subtle that only very sensitive instruments can detect them. What is astonishing is that the current temperature of that radiation background is only about minus 455 degrees Fahrenheit, or about 2.7 Kelvin. This number means it is only a little above absolute zero. Absolute zero is the lowest ideal limit of temperature, where thermal motion reaches the lowest level physics allows. The cosmic microwave background today is so cold that in everyday life we have no direct sensation equivalent to it. But it is not nothing. It is the leftover warmth of the cosmic dawn, stretched and cooled by the expansion of space. We can say, in a very precise sense, that the universe cooled light by expanding itself. When the universe was smaller, the background light was hotter. As the universe grew larger, that same radiation was stretched and became colder. This is not a vague metaphor. It is a measurable physical relationship. The temperature of the cosmic microwave background decreases as the universe expands. Today, that light has wavelengths on the scale of a few hundredths of an inch, or millimeters, which places it in the microwave region. And because it has such long wavelengths, it passes through us without creating any visual sensation. Imagine a very high musical note being stretched gradually until it drops below the range of human hearing. The sound has not necessarily vanished from the physical world, but our ears can no longer hear it. Ancient light is similar, except this is not sound, but electromagnetic radiation. The universe stretched the light note of the beginning until it left the range that human eyes can receive. It is still there, but it is singing at a different frequency, colder, quieter, and deeper in the darkness. This also helps answer a very natural question. If the first light is everywhere, why does it not light up the sky? Because that light is no longer in the visible range. It does not shine like the sun, sparkle like stars, or reflect from clouds like the moon. The energy of each photon has dropped greatly. They do not have enough energy for our eyes to sense them. Night is still dark to our biology, but it is not empty to physics. In that darkness, there is an ancient microwave background covering every direction, like a very smooth thermal mist that only science can read. And right here, we see the beauty of the answer. The first light did not abandon the universe. It changed form along with the universe. It went from hot to cold, from shorter wavelengths to longer wavelengths, from the light of a plasma sea to the microwave background of a mature space. It is like an ancient letter written in hot ink, while over billions of years the paper of space was stretched wider. The words in the letter did not completely disappear, but they spread out, became fainter, and required a different kind of eye to read them. Modern science is that eye. One very deep detail is that the cosmic microwave background keeps an almost perfect blackbody radiation spectrum. That means it is not a random mixture of many modern light sources. It carries the trace of a time when light and matter were once in a strong state of thermal equilibrium. In the early universe, photons constantly interacted with electrons and charged matter, causing the radiation to reach a very distinctive thermal spectrum. After the universe became transparent, that spectral shape was preserved, only stretched and cooled by expansion. This is one of the strongest pieces of evidence for the hot, dense history of the universe. In other words, that microwave background is like an ancient thermometer. It does not only tell us that today the universe has a cold radiation background, it tells us that the universe was once hotter, and if we look backward through the history of expansion, we see a consistent picture. The farther into the past we go, the hotter the background radiation was. The closer to the present we come, the colder it becomes. Modern observations match this with great precision. This is why cosmologists do not treat the cosmic microwave background as merely a beautiful idea, but as foundational data. It is a measurement, evidence, and a physical trace left over from the time when the universe was young. But we also need to be clear that losing energy in this context is not like an object being heated by friction with its surroundings. Light in a vacuum does not rub against space. When we say a photon has lower energy because of cosmic redshift, we're talking about the energy measured by an observer in an expanding universe. This is a subtle detail of general relativity in cosmology. In everyday life, we're used to energy being conserved in a simple way within small systems. But on the scale of the whole universe, in an expanding space-time, the idea of global energy is not always as intuitive as it is in a closed room. What is certain is that observations show the wavelength is stretched, and the measured photon energy decreases accordingly. Let us return to the image of a wave on a rubber cloth. If the cloth becomes twice as long, the distance between the wave crests also becomes twice as long. With the cosmic microwave background, the amount of stretching is far greater. From the time that light was released to today, the universe has expanded by more than 1,000 times, according to the wavelength scale of this radiation. So a wavelength that was once much shorter has become a wavelength on the scale of a few hundredths of an inch, or millimeters. A radiation background that once corresponded to several thousand degrees Fahrenheit, or several thousand Kelvin, has become a 2.7 Kelvin background, which is about minus 455 degrees Fahrenheit. That change alone tells the story of the universe's enormous expansion. If we could place different versions of this radiation on an imaginary table, we would see a quiet but very clear process. In the young universe, the light was hotter, higher in frequency, and shorter in wavelength. In today's universe, the light is colder, lower in frequency, and longer in wavelength. There was no moment when it turned off. There was no place where it fell down. It was simply shifted into another part of the electromagnetic spectrum by the expansion of space. It is like a sentence slowed down until the voice drops very low, while its underlying meaning remains for anyone who knows how to listen. We can also understand this through the colours of very distant galaxies. When a very distant galaxy emits light, that light is also stretched during its journey to us. Because of this, many of the farthest galaxies are observed better in the infrared range, because their original light has been redshifted out of the visible range. But the cosmic microwave background is a much older case. It does not come from a distant galaxy, but from a time before galaxies existed. It has been stretched across almost the entire history of the observable universe, so its redshift carries it from the light of a hot universe into the cold microwave range. This point helps us feel the difference between starlight and the first light. Starlight comes from individual objects, a star, a galaxy, or a region of hot gas. The cosmic microwave background comes from every direction as the shared background of the early universe. Starlight tells the story of individual flames in the cosmos. Background light tells the story of the universe-wide state before those individual flames appeared. So when the background radiation was stretched into microwaves, it was not one separate object changing colour. It was the entire thermal memory of the young universe shifting into a colder form. When scientists measure the background radiation, they do not only measure whether a signal is present or absent. They measure its spectral shape, its temperature, its uniformity, and the tiny deviations across the sky. The average temperature of about minus 455 degrees Fahrenheit, or about 2.7 Kelvin, tells us how much the radiation background has cooled. The tiny fluctuations tell us that the young universe was not perfectly uniform. The nearly black-body spectrum tells us the radiation had a deeply thermal origin. Each feature is one piece of the puzzle. Put together, they create a consistent picture. The first light was stretched by the expansion of space into the cosmic microwave background. Perhaps what makes this story so moving is not only the numbers or the terminology, but the feeling that the past is still passing through the present. A microwave photon passing through your room does not carry warm light like a nightstand lamp. It does not cast a shadow on the wall. It does not make your eyes blink. But it belongs to the same layer of radiation that began its journey when the universe had no sun, no earth, and no living being to call the sky the sky. It is a tiny part of the first morning that physics allows us to observe. Think of the silence of a room at night. You may see everything grow darker, hear sounds grow softer, and feel the world almost become still. But at a deeper level, the universe is still whispering in microwaves. Not a message with intention, not a note written, especially for humans, but the natural result of the laws of physics. That lack of intention is exactly what makes it beautiful. It is honest. It does not exaggerate. It does not tell a story to please us. It simply exists, and by existing, it tells us what the universe was once like. Now, if we ask where the first light is in this room, the answer is not up there, or at some far edge of space. A small part of that photon background is passing through every region of space, including the region around us. Of course, the specific photons that a detector captures come from specific directions in the sky, from the surface of last scattering in the distant past. But that radiation background is not a decoration hanging on the edge of the universe. It is a component of the observable universe, a leftover layer of radiation present everywhere. This leads us to a truth that can make the mind slow down. We do not live after the first light has disappeared. We live inside its aftersound. Every galaxy, every dark gap between stars, every quiet night exists in a universe that still carries that ancient radiation background. It is weaker than starlight to our eyes, but broader than all starlight in meaning. Starlight shows us objects that are burning. The background radiation shows us the thermal foundation of the observable beginning itself. From this point of view, the night sky is no longer a simple black space. It is a many-layered field. The layer human eyes see contains stars, planets, the Milky Way, and sometimes a meteor streak. The layer telescopes see contains distant galaxies, nebulae, galaxy clusters, infrared light, and X-rays. And the deepest microwave layer is the background radiation. Ancient light stretched so far that the eye no longer recognizes it. Each layer is a way the universe reveals its history. But this microwave layer is special because it brings us close to the moment when the universe first became transparent. So where did that light go after 13.8 billion years? It went into the microwave range. It went into the background of the sky. It went into every direction we can observe. It went from a blazing hot state to a deeply cold state. It did not leave the universe but travelled with the universe as space expanded. If we use only our eyes, we think it is absent. If we use physics, we recognise that it is still here. It is light no longer visible to the eye, but still clear enough to measure, precise enough to calculate, and ancient enough to become one of the deepest pieces of evidence for the hot origin of the universe. And here is what makes the story even stranger. That light is not located in one specific faraway place. It is not like a photograph hanging at the edge of the universe. It is arriving from every direction at once. If we point a detector toward the northern sky, we meet it. If we point it toward the southern sky, we meet it there too. If we look through regions where the light from nearby galaxies has been removed, that microwave background still appears. It surrounds our field of view like a sphere of time, not because Earth is at the center of the universe, but because any observer looks backward into the past in every direction. That is the next step of the story. If the first light was stretched into microwaves, why does it come from the entire sky? Why do we not see it only on one side? And why do we call it a background instead of a separate light source? To answer that, we have to step into the way cosmology understands distance and time. Looking far means looking into the past, and looking far enough with light means touching the oldest layer of light the universe allows us to see. If the first light has been stretched into a cold microwave background, the next question becomes very natural. Where is it now? Is it located on the farthest wall of the universe, like a shell of light surrounding everything? If we flew far enough, would we touch it the way we might touch the inside surface of a gigantic sphere? The scientific answer is no. And that very no opens up one of the most beautiful, deepest, and most easily misunderstood ways of looking at the observable universe. The first light is not located at a hard edge of the universe. It is not a curtain of matter hanging somewhere far away. It is also not a wall of light standing still and waiting for us to approach it. It is light that was released everywhere when the universe became transparent, and today, the portion of that light from regions distant enough is reaching us from every direction. When we look up at the sky with microwave instruments, we do not see a single glowing point. We see a background radiation covering the entire celestial sphere, almost evenly, as if the universe were whispering the same ancient memory from every side. To understand this, we need to remember a very simple but extremely powerful principle. Looking far into space means looking back into the past. Light does not reach us instantly. Light from the moon takes more than 1 second to reach Earth. Light from the sun takes about 8 minutes. Light from a nearby star may take many years. Light from a distant galaxy may take billions of years. So a telescope is not only a tool for looking far away, it is a tool for looking into time. Every great distance opens a different layer of the past before our eyes. When we look far enough in visible light, infrared light, radio waves or microwaves, we move closer and closer to the early ages of the universe. But there is a natural limit. We cannot use electromagnetic light to see through the era when the universe was still an opaque plasma, because at that time, photons were constantly scattered by free electrons. That limit is the surface of last scattering. It is not a solid surface, not the cliff edge of the universe, but a layer of time where light was strongly scattered for the last time before beginning to travel freely until today. When we look far enough to reach that layer, we touch the oldest light that electromagnetic radiation can bring back to us. Imagine standing in a wide field on a foggy night. When the fog is still thick, you cannot see far. When the fog clears, light from distant regions begins to reach your eyes. But if the entire field had once been covered by a glowing fog, there would not be one single lamp at the edge of the field. Light would be released everywhere as the fog cleared. The young universe was like that. When electrons joined with protons and the environment became transparent, photons from everywhere began to travel freely. The photons reaching us today are photons from the deepest layer of the past in every direction that we can observe. This point is very important. We are not at the center of the universe. We are only at the center of the observable universe from our own point of view. Any observer in a distant galaxy would have their own observable universe, with themselves at the center of their own observation. This is like standing in the middle of the ocean in fog. The horizon surrounds you in a circle, not because you are the center of the entire ocean, but because your visibility is limited in every direction. In the universe, that horizon is not only a limit of space, but also a limit of time, because light takes time to travel. So when we see the cosmic microwave background coming from every direction, it does not mean Earth sits at the center of a sphere of light. It means that in every direction, if we look far enough into the past, we meet the same era, the time when the universe had just become transparent. The surface of last scattering appears as a sphere around us in the sky, but it is an observational sphere, not a physical shell of the entire universe. It is the place in space-time where ancient light has had just enough time to reach us today. If this is still a little difficult to picture, imagine floating in the middle of a still lake at night. Far away in every direction, ripples are spreading toward you. You hear the water from the left, the right, the front, and the back. You do not conclude that the ocean has a wall of sound surrounding you. You understand that waves can travel from many different regions and reach you at the same time. The cosmic microwave background is similar to an echo of light, but it is not sound. It is ancient light stretched into microwaves, arriving from every direction because the universe once released that light everywhere. A common misunderstanding is to think that the first light is far out there, while the space around us has nothing to do with it. But the cosmic microwave background does not exist only on a sky map like some distant picture. The photons belonging to that radiation background fill the universe today. They pass through the space around us continuously. They are weak, cold, and in the microwave range, so our eyes cannot see them. But physically, they are a real part of the cosmic environment. On average, every 0.061 cubic inch, or every cubic centimetre, of space contains hundreds of photons from this background radiation. That number may sound small, but on the scale of the universe, it is an almost endless ocean of photons. Let us pause for a moment with that image. In a space as seemingly empty as the tip of a finger, there are still hundreds of ancient photons belonging to the early universe. They do not shine like a lamp, they are not hot like fire, and they do not form shapes for the eye to see, but they are particles of light that were released when the universe was still very young and then stretched by the expansion of space. With a sensitive enough instrument, we can recognize that microwave background as a layer of leftover warmth, too cold for human senses to detect, but too clear for science to ignore. This makes the question, where is it, become something entirely different. It is not in one single location. It is in the microwave sky, in the photons arriving from the surface of last scattering in every direction, and in the cold radiation background that fills space. It is far away because its observable origin lies in the very deep past. It is near because its photons are passing through the region of space around us right now. Both far and near, both ancient and present, that is the strange beauty of the first light. We can say, in a very careful sense, that we are living inside the aftersound of the cosmic dawn. Not an aftersound made of sound, because sound needs a material medium and cannot travel through the vacuum of space the way light can. But as a scientific image, the cosmic microwave background is an electromagnetic echo. It is no longer brilliant the way it was when the universe was hot. It has cooled, it has been stretched, and it has become a microwave background. Even so, it still preserves information from the moment when light separated from matter and began travelling freely. When astronomers map that microwave background, they do not see a completely chaotic sky. They see a nearly uniform background in every direction. The average temperature is about minus 455 degrees Fahrenheit, or about 2.7 Kelvin. This means that if we look in different directions, after removing sources of interference such as radiation from the Milky Way, interstellar dust, and closer radio sources, we still see a very even cold background. That uniformity is a sign that the early universe once had a very homogeneous state on large scales. It was not a fire burning in one corner, it was the background condition of the entire observable universe. But that background is not absolutely perfect, it has very tiny differences. Those differences are so important that we will return to them later, because they are clues to the formation of galaxies and large-scale structure. But for now, it is enough to know that the background radiation is both very even and not perfectly flat. It is like a sheet of silk that is almost perfectly smooth, but when examined with an extremely sensitive tool shows gentle ripples. The combination of uniformity and tiny differences is what makes it a newborn map of the universe, not a meaningless screen of light. However, when we look at maps of the cosmic microwave background released by missions such as Planck or the Wilkinson Microwave Anisotropy Probe, we need to understand that the colours in those maps are not the colours human eyes would see if looking directly. The colours are usually exaggerated to represent extremely small temperature differences. Without that exaggeration, the microwave sky would be so uniform that our eyes could not distinguish the variations. So the map is not a photograph in the ordinary sense. It is a scientific translation of microwave data, helping humans see extremely delicate structure in an almost perfect signal. That makes the cosmic microwave background both like a picture, and unlike any picture we are used to, it does not show objects that have already formed, such as stars, planets, or galaxies. It shows the universe before those objects appeared widely. It is not scenery inside space. It is the state of space and matter when light had just become free. If a family photo records a face when someone was still young, then the cosmic microwave background is the picture of the universe in its infancy, before its mature features appeared. And because it comes from every direction, it also shows us that the past of the universe is not located on one special side. When we point a microwave telescope toward one region of the sky, we see ancient light from that direction. When we turn toward another direction, we see that same ancient background again, with very tiny differences. This is one of the strong pieces of evidence that, on large scales, the universe does not give us one special direction, and there is no stage lit from only one side. On large enough scales, the universe appears nearly homogeneous and isotropic. We are not sitting on a central throne. We are small observers inside a vast structure where the laws of physics operate the same way in every direction we can measure. But that smallness does not make human beings less important in the story of understanding. On the contrary, it makes our ability to understand the background radiation even more astonishing. A species living on a small planet, orbiting an ordinary star inside an ordinary galaxy, has built instruments sensitive enough to measure the oldest light in the sky. Not light visible to the eye, not the obvious beauty of a nebula, but a cold microwave background with only very slight differences from one direction to another. That is an achievement of scientific patience, learning how to hear something extremely faint in order to understand something extremely vast. When we ask where the first light is today, we're also asking what the observable universe is. The observable universe is not necessarily the entire universe. It is the part of the universe whose light or signals have had enough time to reach us since the earliest observable era. Beyond the observational limit, there may be many other regions, perhaps enormously vast regions, but light from them has not had time to reach us, or has been limited by the history of expansion. So the cosmic microwave background is not the final edge of all existence. It is the edge of what electromagnetic light from the early universe can tell us. This is like standing in the darkness at night while holding a lamp. The region you can see is not the whole world. It is only the region that your light and your eyes allow you to recognize. In cosmology, the limit is not created by our lamp, but by the speed of light, the age of the universe, the expansion of space, and the time when the universe became transparent. The cosmic microwave background is the farthest layer of information in the past that light can bring us. It does not say there is nothing beyond it. It says that before this point, light could no longer carry clear images to us in the same way. Another way to picture it is to see the background radiation as a horizon of time. On the ocean, the horizon is not a real wall. If you travel toward it, the horizon recedes from your point of view. It is a limit of visibility, not the edge of the water. The surface of last scattering is the same kind of thing. It is our observational horizon through light. If there were an observer somewhere else in the universe, they would see their own surface of last scattering, not exactly the same as ours. This helps remove the mistaken image that the background radiation is a single shell surrounding one special center. What makes the story subtle is that the background radiation is both the farthest place we can see with light and radiation present throughout space. These two things may sound contradictory, but they are not. When we observe the sky, photons arrive from very distant regions in the past, but that kind of radiation itself is a remnant filling the universe. Other photons from the same radiation background exist and move everywhere. We only detect the photons that enter our instruments from specific directions. It is like standing in the rain. You only feel the drops that fall on you, but the rain does not exist only at your location. If the background radiation comes from every direction almost evenly, why are the measurements not exactly the same in every direction? Partly because there are real primordial fluctuations. Another part is that we ourselves are moving relative to the average reference frame of that radiation background. The motion of the solar system and the Milky Way creates an effect called a dipole. One side of the sky appears slightly warmer, while the opposite side appears slightly colder because of the Doppler effect. Scientists have to calculate and remove this effect to study the much smaller primordial fluctuations. That shows that measuring the first light is not simply a matter of looking up, but a very careful process of analysis. We also have to remove closer light. Our Milky Way contains dust, gas, high-energy electrons, and many sources of microwave emission. Other galaxies also add background signals. Without separating these foreground sources, we would not see the ancient radiation layer clearly behind them. So the famous maps of the background radiation are the result of observing many frequencies, comparing data, modelling nearby sources, and separating out the oldest component. This makes the story even more reliable because it does not rest on one simple image, but on many independent and repeated steps of testing. And after all those steps, the ancient microwave background still appears. It does not disappear when we observe it with a different satellite. It is not merely an error from one instrument. It is not only a signal from one direction. It has a distinctive thermal spectrum, a stable average temperature, tiny fluctuations measured again and again, and a deep connection to models of cosmic structure formation. This makes the cosmic microwave background one of the strongest observational foundations of modern cosmology. If we return to the feeling we began with, perhaps the most beautiful part is this: the first light is not out there like some foreign object separated from our lives. It is part of the sky we live under. Our eyes cannot see it, but instruments can measure it. Our skin cannot feel it, but physics can describe it. Our minds cannot grasp it intuitively right away, but mathematics and observation help us reach it. Every dark night, behind that quiet blackness, there is an ancient cold glow passing through space, reminding us that the universe has a hot, dense past, and that it gradually became transparent over time. Imagine someone standing inside an old cathedral at night. All the candles went out long ago, but the stone, the walls, and the air still hold a little warmth from the day that passed. With a very sensitive hand, that person could feel the trace of the light that had once been there. The universe is similar, but on an incomparable scale. The first fires in the sense of stars had not yet appeared when the background radiation was released, but the warmth of the young universe's state remains. It is not held in stone walls, but in the microwave photon background that fills space itself. We can call it fossil light, but we need to understand that it is not fossilized like bone in stone. Fossil bone is matter that once lived, became mineralized, and remained. The background radiation is light still moving. It is fossil-like because it preserves ancient information, not because it stands still. It is not resting in a cosmic museum. It is traveling through space, being measured, arriving from every direction, and carrying within it signs of temperature, density, and early structure. So when someone asks, "Where is the first light today?" the best answer is not to point toward a constellation. It is not to point toward the edge of the sky. It is not to say it is outside the Milky Way or at the end of a straight line. We should say it is in the cosmic microwave background covering the entire sky. It is in the cold photons filling space. It is on the surface of last scattering that we see in every direction. It is in the observational structure of the universe itself, like a layer of light memory that is no longer brilliant but has never disappeared. That answer also explains why we cannot fly to the place where the background radiation is the way we could fly to a planet. If you imagine a spacecraft traveling straight toward the region where we see the background radiation today, then while the spacecraft travels, the universe continues expanding, light continues moving, and the observer on the spacecraft has their own observational horizon. The background radiation is not a fixed place to land. It is a layer of the past seen from the position and time of the observer. Moving somewhere else does not take you outside the story. It only gives you another viewpoint on the same universe. This is very different from everyday intuition. In daily life, if we see a mountain far away, we can walk toward it. If we see a wall, we can touch the wall. But in cosmology, some things are observational limits, not objects we can approach. The surface of last scattering is such a limit. It appears in the sky because light from that era has just reached us. It is not the final wall of space. It is the final curtain of electromagnetic light when we look backward into the past. When we understand this, we can gently let go of the simple idea of an edge of the universe. The observable universe has a limit, but the entire universe may be far larger than the part we can see. It may not have an edge in the familiar sense. Science does not need to imagine an outermost wall to explain the background radiation. What we need is the expansion of space, the early hot and dense state, the opaque era of the universe, the formation of neutral atoms, and the freedom of light to travel. Those elements are enough to create the microwave background coming from every direction. So where did the first light go? It went into the entire observable history of the universe. It went into the sky background that every microwave telescope must face. It went into cold photons, hundreds of photons in every 0.061 cubic inch, or every cubic centimetre, of space. It went into the oldest thermal map science can create. It went into a kind of darkness that is not truly empty, where human eyes see only night, but measuring instruments see the trace of the time when the universe began to become transparent. And right here, the story becomes strangely intimate. When you sit still in the dark with no need to see anything special, and no need to imagine yourself flying through galaxies, you are still inside the same universe that contains that ancient radiation background. On the human scale, everything may feel very quiet, but on the cosmic scale, that quietness has a depth of 13.8 billion years. It is not loud, it is not dazzling, and it does not demand our attention. It is simply there, a cold background surrounding every direction, like a memory too ancient to shine brightly, but too real to vanish. From here, we're ready to move into the next important part. If that light is present across the whole sky, what has it told us? Why are the tiny differences in its temperature so important that scientists use them to understand the birth of galaxies, stars, planets, and eventually ourselves? Because the cosmic microwave background is not only the oldest light, it is also the newborn map of cosmic structure. Within that almost uniform coldness, there are very small ripples, and within those ripples are the seeds of every great shape the sky would later take. Now we know that the first light is not located on some distant wall, but is arriving from every direction as a cold microwave background covering the sky. But if we stop there, we understand only half the story. The other half goes much deeper. That ancient background of light is not perfectly smooth. It is almost uniform to an astonishing degree, but within that almost, there are incredibly tiny ripples. And those tiny ripples are one of the reasons the universe today is not just a smooth fog, but has galaxies, stars, planets, rock, water, and eyes looking back toward their own origin. Imagine a wide lake just before dawn. From far away, it seems completely still. But when you lean in very close, you see faint ripples moving across the surface so small that without moonlight reflecting on them, you might miss them. The cosmic microwave background is similar. Its average temperature is almost the same in every direction, about minus 455 degrees Fahrenheit, or about 2.7 Kelvin. But when sensitive enough instruments measure small regions of the sky, they detect temperature differences of only millionths of a degree. In everyday life, that difference means almost nothing. In cosmology, it is the first set of brushstrokes in the sketch of the entire structure of the universe. What moves scientists is not that this microwave background has beautiful colours in published maps. Those colours are usually exaggerated so human eyes can recognise them more easily. What truly matters is that behind each slightly warmer or slightly colder region, there is a physical story. Those differences reflect extremely small fluctuations in the density and energy of the young universe. In one place, matter was just a little thicker. In another, it was just a little thinner. That difference was so small that, by intuition alone, we might think it could never create anything grand. But the universe has one very patient worker: gravity. Gravity does not need a huge difference to begin working. A region only slightly denser than its surroundings can already pull in matter a little more strongly than nearby regions. At first, the effect is very weak. But cosmic time is not a few seconds, a few years, or a few centuries. It is hundreds of millions of years, then billions of years. A small difference, nourished by gravity for long enough, can become a larger cloud of gas. That cloud can contract. Denser regions can give birth to stars. Stars gather into galaxies. Galaxies gather into clusters. Galaxy clusters lie within a cosmic web so vast that the human mind can barely picture it. So within the oldest light, there is the first draft of cosmic structure. It is not a map of fully formed galaxies. It does not show us the spiral shape of the Milky Way. It does not point to the location of Earth, and it does not say where oceans or life will appear. But it shows us the initial conditions, the extremely small differences from which the universe could develop into a place that is uneven, structured, and deep. Without those tiny ripples, the universe might have been too smooth, and then there would have been no clear starting point for gravity to gather matter into stars and galaxies. Here, we need to speak very carefully. It is not that every hot or cold spot on the background radiation map becomes one specific galaxy. The universe does not work as simply as marking each seed and then watching it grow into a separate tree. The fluctuations in the background radiation are statistical traces of the initial state. They tell us about density distribution, about the motion of photon and baryon plasma, about gravitational wells partly created by dark matter, and about acoustic oscillations in the young universe. From there, scientific models can calculate how matter developed into large-scale structure, but the path from one tiny ripple to one particular galaxy is still a long and complex process. A more accurate image would be to imagine the background radiation as an extremely early topographic map of a land where no cities have been built yet. Slightly higher places, lower places, or sloped places are not houses, roads, or forests, but they influence where water will flow, where soil will accumulate, and where valleys and rivers may form later. In the young universe, tiny density differences were not galaxies, but they influenced the direction matter would fall, where gas would gather, and where gravity would quietly amplify a tiny imbalance into large structure. To understand why those ripples appear in the microwave background, we need to return to the time when the universe was still a tightly coupled mixture of light and ordinary matter. Photons created radiation pressure. Matter, especially dark matter, created gravity. A slightly denser region tended to pull matter inward, but hot radiation pushed back against compression, creating oscillations similar to pressure waves in the early plasma. We can call them acoustic oscillations, but we should not imagine sound in the sense of something human ears hear in air. These were density oscillations in a hot cosmic medium, where light and ordinary matter were still interacting very strongly. When the universe became transparent, those oscillations were preserved as a pattern in the microwave background. Light began to travel freely, carrying with it the trace of the final state before it separated from matter. So the cosmic microwave background is like a photograph of an extremely ancient moment, in which the ripples of the primordial plasma were recorded. Not a photograph taken by an ordinary camera, but a photograph made of temperature, microwaves, and differences of only a few millionths of a degree. The more precisely we measure those ripples, the more we understand how the young universe oscillated, compressed, expanded, and distributed matter. This is why missions such as the Wilkinson Microwave Anisotropy Probe and Planck have been so important. They did not only look for whether the background radiation existed, that had been confirmed long before. Their deeper mission was to measure its extremely tiny fluctuations across the entire sky with very high precision. Planck was designed to observe the background radiation at many wavelengths, separate the ancient signal from closer sources of emission, and create one of the most precise maps of the universe's baby light. Every time the precision improves, our picture of the young universe becomes clearer. But that map is not beautiful only because it is ancient. It is beautiful because it can be tested. Science measures the angular size of the ripples, measures their strength, measures how they are distributed across different scales, and then compares them with cosmological models. From that pattern, we can infer many things: how nearly flat the universe is on large scales, how much ordinary matter there is, how dark matter affects structure, what role dark energy plays in later expansion, and how the age of the universe fits with about 13.8 billion years. In other words, the cosmic microwave background is not only a keepsake, it is a laboratory spread across the whole sky. In that laboratory, each tiny temperature fluctuation is a measurement of early physics. Any model of the universe that wants to stand must explain why the microwave background has its average temperature, why it is almost uniform, why it has tiny differences at that level, why those differences are distributed in that pattern, and why those patterns connect to the galaxy structure we see later. One of the most astonishing things is how small those initial differences were. Imagine a very large room with almost exactly the same temperature at every point, differing by only a few millionths of a degree. In everyday life, we would never be able to feel it. But if that room were the early universe, and if the time ahead were billions of years, then those few millionths would become the initial conditions for all later architecture. That is the subtlety of nature. The universe does not need to begin with giant walls. It can begin with ripples that are almost invisible. The role of dark matter in this story is also very important, but it needs to be explained just enough and accurately. Ordinary matter, meaning the matter that makes atoms, stars, planets, and our bodies, was still strongly affected by radiation before the time of recombination. It was pulled along by light in the hot plasma. Dark matter, according to current understanding, does not interact significantly through electromagnetism, so it could help create early gravitational wells. After light separated, hydrogen and helium gas could fall deeper into those gravitational regions. Without dark matter, the formation of structure as we see it would be harder to explain in the modern model. However, the universe did not immediately have stars after the microwave background was released. There was a period often called the Cosmic Dark Ages, not because there was no background radiation, but because there were not yet stars and galaxies shining strongly in the visible range. Neutral gas gradually gathered. Gravity worked slowly. Large gas clouds grew, cooled, contracted, and after a long time, the first stars began to shine. So the background radiation became the bridge between the age before stars and the age of luminous structure. But there are still limits we need to keep clear. The background radiation does not answer every question. It does not directly tell us what the absolute first moment of the universe was. It does not prove every detail of cosmic inflation in an absolute sense. It does not replace observations of gravitational waves, dark matter, or dark energy. It is the oldest light we directly observe through electromagnetic radiation, and it is an extremely powerful source of information about the universe when it was about 380,000 years old. Before that, we have to reason indirectly through models, data, and remaining traces. Let us return to the image of the lake. If the lake surface were perfectly flat with no ripples, we would not know how the wind had passed over it or how the water was moving. But if there are tiny ripples, a patient observer can read a great deal: the wind direction, obstacles beneath the water, and deeper motion below. Cosmologists read the background radiation in a similar way. They do not read it to find a familiar picture. They read it to understand the initial conditions. Those ripples are not scenery, they are clues. And because those clues stretch across the whole sky, they give us a global view of the early universe. There is a very peaceful beauty in this idea. Every enormous structure began from near uniformity. The young universe was not chaotic in the sense that everything was randomly shattered. It was deeply uniform but not absolutely perfect. And that tiny imperfection is what allowed the story to continue. If everything had been too smooth, there would have been no seeds for gravity to amplify. If everything had been too chaotic, we might not have the orderly universe we observe. The universe seems to have begun with a delicate balance, uniform enough to have general laws, rippled enough to give birth to structure. When we look at the map of the background radiation, we are looking at a time before familiar objects existed, but after the conditions for those objects had been laid down. It is like looking at a piece of music before the orchestra has fully begun to play. The main themes are already there. The underlying rhythm is already there. The later variations have not appeared yet, but their possibilities are already held in the initial structure. Gravity, time, gas, dark matter, stars, and galaxies will continue that music. But the first tones, very thin and very soft, were recorded in the microwave background. And then, over time, the universe began to shift from a thermal map into material architecture. Slightly denser regions pulled in more matter. Gas fell into gravitational wells. Where density became high enough, gas heated up, cooled through radiation processes, contracted, fragmented, and eventually formed stars. The first stars lived, burned, created heavier elements in their cores, and some ended in violent explosions. Those elements entered later generations of stars, rocky planets, water molecules, and complex chemistry. That whole process is not drawn in detail in the background radiation, but it began with a universe that had small differences for gravity to hold onto. We can say, in gentle language that still stays scientifically true, that the cosmic microwave background is where the universe left the first sketch of its future. Not a future that was predetermined in every detail, but a future that could develop from initial conditions. Within a small ripple of density, there was no specific star's name already written, but there was probability, motion, gravity, and evolution. The universe did not write every individual story in advance, but it set the laws and conditions that allowed those stories to happen. This makes the first light feel closer to us than we might think. It is not only the ancient background behind the galaxies, it is the beginning of the chain of causes that led to an environment where galaxies could form. Without density ripples, there would be no stars as we know them. Without stars, there would not be abundant heavy elements. Without heavy elements, there would be no rocky planets like Earth. Without stable rocky planets in the right kinds of environments, there would be no oceans and complex chemistry as we know them. When we look at the background radiation, we do not see life, but we do see one of the very early physical conditions that later allowed the universe to have places where life could appear. Of course, we should not turn this story into mystical destiny. Science does not say that the background radiation wanted to create us. The universe does not need intention in order to produce structure. The laws of physics, initial conditions, time, and probability were enough to create richness. The wonder is not in intention, but in the fact that unconscious laws can still lead to a universe so complex that observers can exist within it. The first light does not send a private message to anyone, but it preserves a record that intelligence can learn to read. So when we ask why that light is the baby map of the universe, the answer is this: because it records the state of the universe at the moment when light had just separated from matter, with extremely tiny temperature fluctuations reflecting the earliest density differences, and those differences through gravity and time became the seeds of large-scale structure. It is a map not because it draws galaxies that already existed, but because it draws the conditions that allowed galaxies to be born. It is a baby map not because the universe began exactly at that moment, but because it is the oldest light image of the universe that can still reach us. Now, if we look back over the whole journey, we see a very clear chain. First, the universe was hot and opaque. Then it cooled, neutral atoms formed, and light became free. After that, expansion stretched that light into microwaves. Today, the microwave background arrives from every direction, not as a wall at the edge of the universe, but as a time horizon of ancient light. And within that microwave background are tiny ripples, the first sketch of structure. From light to microwaves, from microwaves to a map, from the map to galaxies, this story shows that the past does not disappear. It is rewritten into a form that science can measure, and that is why the cosmic microwave background is not only the answer to the question of where the first light went, it is evidence that that light became the widest memory of the observable universe. It no longer shines for human eyes, but it shines for intelligence. It is no longer hot like it was in the beginning, but it is still warm enough to tell us about a hotter time. It is almost still, but within that stillness are ripples that led to every structure. If any map deserves to be called the baby map of the universe, it is this cold, ancient, silent, and deeply informative microwave background. After everything we have gone through, the first light no longer feels like a distant idea. It is not just a layer of cold radiation sitting in astronomy books. It is evidence that the universe has a past we can measure. When we observe the cosmic microwave background, we are not only looking across an enormous distance, we are looking at the youngest version of the universe that light can still bring back to us. That is a very deep thing. The universe is not only vast, it also has memory. Not memory the way humans remember a face, a voice, or an evening that has passed, but memory stored in temperature, wavelength, direction of travel, and the tiny fluctuations of light. The first thing that makes this light important is that it helps us know the universe was once much hotter and denser. This is not a story imagined simply because the sky feels mysterious. If the universe was once in a hot, dense state, then expanded and gradually cooled, we would expect a cold, almost uniform background radiation to remain, coming from every direction. And that is exactly what scientists observe. The cosmic microwave background is the thermal remnant of the young universe. It is like a very faint warmth left behind after a furnace has cooled over an unimaginable stretch of time. The flame is no longer visible to the eye, but the delicate thermometer of science can still read its trace. That is why the cosmic microwave background is one of the great pillars of the hot Big Bang model. It does not stand alone, because science always needs multiple independent lines of evidence. The expansion of the universe, the proportions of light elements such as hydrogen and helium, the distribution of galaxies, and the cosmic microwave background together form a consistent picture. But among those pieces of evidence, the microwave background has a special quality. It is the oldest light we can observe directly through electromagnetic radiation. It does not only tell us that the universe is expanding today, it shows that the universe once had a specific thermal state in the deep past. From that radiation, humans have also measured the age of the universe with astonishing precision. The number of about 13.8 billion years was not chosen because it sounds beautiful or mystical. It comes from combining many measurements, with the cosmic microwave background playing an extremely important role. The pattern of fluctuations in the microwave background is like an ancient code. When scientists decode it, they can infer the expansion rate, the amount of ordinary matter, the amount of dark matter, the influence of dark energy, and the overall geometry of the universe on large scales. From there, the age of the universe appears not as a vague guess, but as the result of a careful system of measurement. This is worth thinking about. A cold, almost uniform radiation background so weak that human eyes cannot see it can help us measure the age of the entire observable universe. It is like looking at a very fine layer of ash and inferring the temperature of an ancient fire, the time that has passed, and the structure of the room where that fire once burned. In everyday life, we often think weak things are less important. But in astronomy, a weak signal is sometimes the most precious signal because it is less noisy, less showy, and comes from the deepest layers of time. The cosmic microwave background also helps us understand what the universe is made of. The tiny fluctuations in the radiation background do not only tell us that some regions are slightly warmer and others slightly colder. Their pattern depends on the amount of ordinary matter, and dark energy in the universe. Ordinary matter is the part that makes atoms, stars, planets, rock, water, and living bodies. Dark matter does not shine in a way we can observe directly with light, but its gravitational effects strongly influence how structure forms. Dark energy is the name given to the component connected with the accelerated expansion of the universe in later times. These things may sound distant, but their traces appear in the way the microwave background fluctuates. We can picture the background radiation as the echo of a cosmic bell, but this bell is not made of metal. It was the hot plasma of the early universe, where light and ordinary matter were still tightly linked. When the universe was young, pressure waves moved through that medium. After light separated from matter, the pattern of those oscillations was preserved in the microwave background. If the bell had more ordinary matter, the echo would be different. If there were more dark matter, the rhythm of the oscillations would also be different. If the geometry of space were different, the angular size of the ripples in the sky would change as well. So the microwave background is not only ancient light. It is a test of the entire model of the universe. It is important not to turn these concepts into statements that are more certain than the data allow. Dark matter and dark energy are still great mysteries. We know them through their effects in observations, but their deeper nature is still not fully understood. The cosmic microwave background helps measure and constrain these components within the modern cosmological model, but it does not make every mystery disappear. On the contrary, it gives us a clearer map of what we still do not know. Science is powerful not because it has answers to everything, but because it knows how to measure the limits of its answers. The first light also helps us understand the formation of galaxies in a humble and beautiful way. Before there were stars, there were tiny ripples in density. Before there were galaxies, there were very slight differences in the young universe. The background radiation records those ripples. Later, gravity amplified them into regions where matter gathered. Gas fell into gravitational wells. The first clouds of gas contracted. The first stars ignited. Galaxies gradually formed. The background radiation is not a photograph of galaxies, but it is a map of the initial conditions that allowed galaxies to be born. It is like looking at the very early foundation plan of a city before the city had streets, lights, houses, and human voices. And if we look even deeper, that light helps us ask questions about eras even earlier than itself. The cosmic microwave background is the farthest limit that electromagnetic light can take us directly into the past. But before the universe became transparent, there are still many things to understand. Why was the universe so astonishingly uniform across regions that were extremely far apart? Why did the initial fluctuations have the pattern they did? Did the universe go through a period of extremely rapid expansion called cosmic inflation? If so, where exactly are its traces? The microwave background does not answer everything completely, but it asks the right questions, and in science, the right question is sometimes as valuable as an answer. One of the most subtle areas of research is the polarization of the cosmic microwave background. Light does not only have temperature and wavelength, it also has a direction of oscillation in its electromagnetic field. When photons scattered in the early universe, they could create very weak polarization patterns. Scientists study those polarization patterns to understand more about early structure, about how light interacted with matter, and even to search for indirect traces of very early processes. This work is difficult because the signal is weak. There are many sources of noise and errors have to be controlled with extreme care. But that difficulty is exactly what makes it valuable. The weaker the signal, if measured correctly, the more it may come from a very deep layer of the past. We also need to remember that the background radiation is not only important in laboratories or scientific papers. It matters because it changes the way we feel the sky. When they are young, many people look at the night sky and think, the space between the stars is empty darkness. But science shows that darkness has depth. There is visible light from stars. There is infrared light from warm dust. There are radio waves from high-energy sources. And deeper still, there is the ancient microwave background, cold, even, and silent. The sky is not only the space above our heads, it is an archive of time. If someone stands under the night sky and asks, "What am I looking at?" the simple answer is stars. But the deeper answer is, you're looking at many layers of time stacked on top of one another. Some light left stars a few years ago, some left galaxies millions of years ago. Some comes from more distant galaxies when Earth did not yet have its present form, and behind all of it, at the limit of observable light, is the microwave background from when the universe was only a few 100,000 years old. In that way, the night sky becomes a book that is not read by pages but by wavelengths. This makes the question, where did the first light go, both scientific and human. It is not only asking about the location of photons, it is asking whether the past still leaves traces, and the answer is yes. The past of the universe has not been completely erased. It has been spread thin, cooled, and stretched into microwaves, but it can still be measured. A very ancient state left a trace in the present. That makes the universe unlike a stage where every old scene disappears completely when a new scene begins. The universe is more like a long piece of music, where the first notes still create the background tone for later movements. On an emotional level, the cosmic microwave background reminds us that everything familiar came very late. Our sun was not present when that light was released. Earth did not exist. There were no oceans, mountains had not risen, forests had not grown, no living thing was looking up, no language existed to call it light. But the photons had begun their journey, and after billions of years, in a universe with galaxies, stars, planets, and life, those photons can still be encountered with scientific instruments. There is something deeply peaceful in that continuity. But that peacefulness should not make us forget precision. The background radiation is not a soul of the universe in a mystical sense. It is electromagnetic radiation that can be measured, with a spectrum, a temperature, fluctuations, polarization, and a physical origin. The wonder lies in the fact that these entirely physical things are deep enough to awaken emotion. Nothing needs to be added beyond the truth. Light from the young universe still fills space. It has been stretched into microwaves. It comes from every direction. It carries within it a record of the initial conditions, and it helps us understand why the universe today has such a rich structure. The background radiation also teaches us a lesson about how science sees the invisible. To the naked eye, it has no colour. To human sensation, it has no heat. In everyday life, it almost seems not to exist. But when humans build receivers, satellites, methods of analysis, and mathematical models, the invisible becomes data. It is like someone learning to hear a very low sound in the wind. At first, there is only silence. After years of training and with the right tools, that person recognizes a steady rhythm within the silence. Science has done this with the microwave sky. Perhaps that is why the cosmic microwave background has such a strong hold on curiosity. It is not just an interesting fact. It is a doorway into many of the biggest questions. What state did the universe begin from? Why does it expand? What is it made of? Why is there structure instead of absolute uniformity? Is space flat on large scales, or curved in some way? What happened before light could travel freely? These questions are not meant to confuse the mind, but to help us see that we stand before an order far larger than everyday intuition. When we say the background radiation helps test the Big Bang model, we should also understand the word test correctly. Science does not only look for data that confirms what it likes. Science puts models at risk of being wrong. If the background radiation did not have the predicted temperature, if it were not almost uniform, if its spectrum did not resemble blackbody radiation, if its tiny fluctuations did not fit the observed structure of the universe, the model would have to change deeply. But observations match very strongly. That does not bring science to an end. It gives us a stronger foundation from which to ask more subtle questions. There is a humble beauty in this. The universe does not give us answers in giant letters across the sky. It gives us a weak microwave background, fluctuations of a few millionths of a degree, an almost perfect thermal spectrum, and asks us to be patient. Humans had to learn mathematics and physics, build instruments, launch satellites, remove interference from the galaxy, check errors, and only then could we read the story. And when we read it, the story does not only say, "This is old light," it says, "This is an early state of space, matter, and energy. From here, every familiar structure will gradually appear." The background radiation is also important because it gives us a cosmic reference frame. We move through space along with Earth, the Sun, the Milky Way, and the local group of galaxies. That motion creates a dipole signature in the microwave background. One direction appears slightly warmer, and the opposite direction appears slightly colder. By measuring and correcting for that effect, scientists can understand our motion relative to the average background radiation. Once again, ancient light does not only tell us about the past, it also helps locate our present within the vast universe. Still, the deepest thing is the feeling of origin. When we look at a rock, we see matter that has passed through geological history. When we look at a drop of water, we see molecules made from atoms with cosmic origins. When we look at a star, we see an enormous nuclear furnace. But when we look at the cosmic microwave background, we're no longer looking at one specific object. We are looking at the background of all objects. We are looking at the time before the universe had familiar shapes. It is like looking not at sentence in a book, but at the first page where the story could begin to be written in light. This does not make humans the center of the universe. On the contrary, it reminds us that we are very late, very small, and very new. But at the same time, it shows that intelligence can connect itself with very deep time. A biological brain that exists for only a few decades can understand a signal that has travelled through almost the entire history of the universe. Eyes that cannot see microwaves can build tools to see what eyes cannot see. A short human life can touch a question 13.8 billion years long. That is not human arrogance. It is the gentleness of understanding. When we observe the cosmic microwave background, we do not see the absolute first moment itself. We see the farthest limit electromagnetic light allows, the universe when it had cooled enough to become transparent. But that limit alone is deep enough to change everything we think about the sky. Before that, the sky might have seemed like a place where stars simply hang. After that, the sky becomes a lake of time, where each wavelength is a different depth. And at the deepest layer of observable light, the microwave background still rests quietly. So the question of why the first light still matters to us today is not only about measuring this number or testing that model, it matters because it gives us a more accurate way to understand our place. We do not live in a young universe that has only just begun, and we do not live in an empty, meaningless darkness. We live in a universe with history, traces, structure, and evolution from simplicity toward complexity. The first light is one of the oldest witnesses to that history. And so, the question, where did the first light go, has an almost poetic answer. It went in every direction, through every age, through the birth of galaxies, stars, and planets, until it finally became a silent layer surrounding the very observer who studies it. It is no longer light human eyes can see. It is no longer hot as it was in the beginning. It no longer stands out in the night sky. But it is still there, in the cold microwave background, in delicate maps, in the numbers that measure the age of the universe, and in the tiny fluctuations that speak of the seeds of structure. If we listen to that answer calmly, we see that it is not only about light. It is about the persistence of traces. Something that happened very early can leave consequences that last for a very long time. A small fluctuation can become a galaxy. A weak radiation background can become powerful evidence. A past so distant that it is almost impossible to imagine can still touch the present through cold photons. And a simple question, if followed deeply enough, can open the entire history of the observable universe. Now we can look back from the beginning to here as if looking at a long river. At first, the universe was hot, dense and opaque. Light was present, but not yet free. As the universe expanded and cooled, neutral atoms formed, and photons escaped constant scattering. Light became free. Then the expansion of space itself stretched its wavelengths, cooling it into microwaves. That microwave background comes from every direction, not as a wall at the edge of the universe, but as a time horizon of ancient light. Within it are tiny ripples, the first sketch of structure. And because of it, we can measure the age of the universe, test cosmological models, study what the universe is made of, and ask questions about even deeper eras. That is why the first light still matters. It is not only the remnant of a lost past, it is a foundation of evidence for the present. It is the bridge between the young universe and a universe with observers. It shows that the past is not separate from the present, but is still flowing through the present as very cold photons. And if tonight the sky seems dark, we can remember that blackness is not the final emptiness. Behind it is an ancient layer of light, too faint for the eye to see, but deep enough to tell the childhood story of the universe itself. So after this long journey, we have followed the trace of one of the most beautiful questions in cosmology. Where did the first light of the universe go after 13.8 billion years? And the answer is not that it went out, nor that it vanished into some distant corner of space. It is still here, but it has changed form. From the hot light of a young universe, the expansion of space stretched its wavelength, cooled it down, and turned it into the cosmic microwave background, an ancient, cold, faint layer of light covering every direction of the sky. We have understood that the early universe was not dark at all. It was once a blazing but opaque ocean of plasma, where photons constantly collided with free electrons and could not travel far. Then, as the universe cooled after about 380,000 years, electrons joined with protons to form neutral atoms. The cosmic fog gradually cleared, and light became free to travel through space for the first time. That light did not come from a star because stars had not yet been born. It was the light of the young universe itself, the oldest light that science can observe through electromagnetic radiation. And we have also seen that the darkness out there is not truly empty. Behind the quiet blackness of the night sky is a cold microwave background, almost uniform yet still carrying tiny ripples. Those ripples are traces of the earliest unevenness, the seeds that gravity amplified over billions of years to create galaxies, stars, planets, and eventually observers who can wonder where they came from. So if tonight you look up at the sky and see its silence, remember that this silence is not complete absence. On a deeper layer than human eyes can see, the universe still preserves its newborn light, a light that has travelled through almost the entire history of the universe. Not loud, not brilliant, but enduring like a physical memory written in temperature, wavelength, and time. Thank you for joining Drift into Quiet. Knowing through this gentle journey, now, let your mind rest. Let the great questions settle down like light fading into space. I wish you a deep and peaceful sleep, and I will see you again in the next quiet journey of knowledge.